So, hello, welcome to Firetie. Today we have with us Kishor. After a long delay, we are back and he will talk about, he will resume the revision of mechanics from the book Landau. And over to Kishor.
Okay, let's talk about interactions of the integration of the equations of motion. And
Kishor, I can't see the slides.
yeah, I need to close it. So yeah, I should be good. Can you see now?
Not yet. I can still see your face. Right.
Can you see it?
Okay, I can see it
Can you
now.
see it?
Yes. I, yes, yes.
So let's talk about
Okay.
motion in one dimension.
It would
So,
it would help if you could fit the page width. I mean, if you could zoom a little. Or just pinch and zoom. Okay, you can do that. Okay, cool. Okay.
yeah. So motion of a system with 1 degree of freedom is said to take place in one dimension. Yeah.
Okay.
So the most general Lagrangian for such a system will be given by obviously the kinetic term and the potential term. And since you have just 1 degree of freedom, you have Q and the corresponding what do you call it, Q dot, where AQ is a function of.
Kishore, zoom it out. No, sorry. It's you have to move. Just fit the page width. Don't zoom further than that. Enough. Okay. Okay, that something happened.
Yeah, is it okay now?
Yeah, okay. Yeah, it's fine. Thank you. And also, I wanted to tell you that we have already done this part, so you just have to quickly recall this and move on to the part we
Okay.
haven't done. Okay.
So AQ is some function of Q. Now, if Q is the Cartesian coordinate, then we can simply write AQ becomes mass and Q dot is x dot. So it's half mx dot square minus u of x. So we need not even write the equation of motion. Let's start with energy equation. First integral. So we integrate this one, and yeah. So you get half mx dot square plus ux equal to e, and from there you can get dx by dt equal to e minus ux by m in times under. Okay, and from here you can then calculate x as a function of time, so t as a function of x. So two constants there. So we have here two constants e and this constant of integration. Now, since half mx dot square is greater than equal to 0, then so it implies that e should be greater than equal to u of x. That should be obvious from the fact that it's under the under root, right?
It could have negative energy also. So
Yeah, it could have negative energy, but then
it is possible that U is greater, no? Like, and so E can be less than U also, right?
you're saying that u is, yeah, but in any case, like even if u and e both are negative, even then e should be greater than equal to ux.
So one term is positive, you're adding a positive term. Yeah, it has to be. Yeah. What was your problem?
So
Sorry, I didn't understand.
is that since half mx dot square is greater than equal to 0,
Yes.
so this since term is the problem. Like this thing implying that e should be greater than equal to ux. I'm saying that this is obvious from the fact that it's under root. So
So it's the same thing. Under root means what? That you have a square term. It's the
yeah,
same
yeah,
argument. No?
yeah. So from the from square thing we got the under root. So, yeah. Okay. So when e is equal to e, we get the limits of the motion. Yeah. Yeah, then we get the singularity and all. These points are called turning points.
Okay.
Okay. So
Yeah.
finite, we define as when the region of motion is bounded by two such points. This is what the motion is said to be. Okay. So if there are two such points, then we call it finite motion. Infinite, if
Okay.
the region of motion is limited on only one side or neither, then the motion is said to be this infinite.
Okay.
Yeah. So in one dimension, a finite motion is oscillatory. It should be oscillatory, but yeah. How do we define oscillatory motion? Like the period need not be uh, constant, right?
Yeah, oscillatory, I think it just means the English word that it comes back and forth, goes back and forth. They haven't defined it right, so it must be English only.
Okay. So in one dimension, a finite motion is oscillatory. Yeah, right. It will go come. The time period then is said to be the time to go from x1 to x2.
Twice,
Okay,
twice the time.
twice. Yeah, yeah, twice. Clear from both the integral and the time reversibility. So from there you get the this thing as from x1 to x2 under root 2m, and where x1 and x2 are the root of ux equal to e. Okay. So
Can you,
this is
Kishore, please explain how it is clear from the integral and the time reversibility? I'm not sure.
so so from it's
Acha,
two times
okay.
because
ठीक है.
we were
You change the limits and you change the sign of dx and it will give you the same answer, right?
yeah or yeah basically you are saying the same thing, like if you repeat this thing back, it is same as changing the limit, and to change dx, then it should give the same answer. So that is basically that comes from time reversibility, right?
No, that I didn't see. I just from this expression that time te is given as x1 to x2 dx, which doesn't have any time dependence, I could understand, but I did not understand the time reversibility argument.
Yeah. So time reversibility means you change t to minus t.
Hmm.
So x of t will go to x of minus t.
Okay. So
So that basically implies that if it was at x1 at time t,
yes.
uh,
Oh, huh, I think I remember now. So Deshna
so
ma'am had taught us that if you send t
because
to
of the time
minus t and
reversibility,
x
you are
to
getting
minus x, it becomes the same. No?
Atul, because of the time reversibility, you are getting two times the same thing.
Array,
So
that you can see in two different ways. One is that you see from x1 to x2 and then from x2 to x1. Both of them
yeah,
will take the same amount of time. That is one. But
yeah.
in
So
that argument, there is no time at all. It's only in the left hand side that you have the time which you're trying to calculate. But it doesn't play a role in the argument since you are only looking at coordinates and integrals of coordinates. But in the other argument, it's saying that time reversibility plays a role in the argument, which means that, as far as I remember, Sudeshna ma'am said that if you put t to minus t and x to minus x, the equation of motion are invariant, which means all results you get will be invariant. So I think that is what we have to use, right? अरे dx by dt है ना, तो dx भी नेगेटिव कर दे, dt भी नेगेटिव कर दे, तो इक्वेशन सेम ही रहेगा, बट तेरा मोशन पूरा रिवर्स हो गया,
yeah,
समथिंग लाइक दैट, बट आई एम नॉट श्योर.
what I was thinking, like x1 से x2 में कुछ time लग रहा है, and then if you reverse it back, then the same time should take, because you are just
That is the conclusion. You have to show why it holds.
yeah. So basically, when you are making dx by dt negative by making t going to minus t, right?
Yes. Yes.
Okay.
But anyway,
So
okay, we'll see what that does later. Okay.
so uh, so this is u equal to e curve, and these are the limit points. Okay.
Hmm.
So the motion in this region will be oscillatory. Motion in this region will also be
What is the
oscillatory.
definition of this, Kishore?
That it should be bounded by two limit points.
No, no. How are you? What? How are you specifying the regions?
Regions that the region should be bounded by 2 points where U equal to E.
Ah, that I know. But you were saying this region is bounded. This region is not bounded. How do you
No, no, I'm saying
characterize this?
uh, this region is and that I was like thinking from the fact that here U is greater than E and here U is less than E.
Mm. So you mean the region AB and BC, something like that?
Yeah, yeah, A, B, and B, C. Yeah,
Ah, okay.
does it make sense?
Yeah, yeah, it's fine. I just couldn't understand what this meant. You were not
Okay.
specifying what region you're looking at. That's all.
Okay. So the next
Hmm.
thing is the determination of the potential energy from the period of oscillation. Okay.
Okay.
So in our earlier case, we calculated the time period. Now, once you know the time period, how you calculate the potential energy. So
Mhm.
given period of oscillation t as a function of E, we wish to find U of x.
Hmm.
Mathematically, then we want to solve t of E equal to under root 2m, this thing, where t is unknown and ux is unknown. We start with assuming that ux has only one root, which means minima in the region x1, x2. Okay.
Mm-hmm.
We aren't considering solution that may exist which don't satisfy the said condition. Okay. Uh, Start with something with only one root.
Meaning it's possible that you had so
More
you
than
had
one root.
multiple minima and you still have oscillation between x1 and x2.
Yeah, yeah,
So
yeah.
we are not
Awesome.
taking that case. That's all it's done.
Mhm. Further, for convenience, we choose the origin at the position of minima. Okay. So you have written that intuitively it's clear. Mathematically, so long as the field is not dependent on time, you can write the energy conservation in terms of in in
In the
translated
translated
coordinate.
quadrant. Hmm.
So you can just shift it. So yeah, it's okay. So uh, further we take this minima to be zero. The equation of motion does not depend on arbitrary constant added to U.
Yes.
Arbitrary constant added to U. Why not? Because yeah, then x1, the position of x1 and x2 will depend on the arbitrary constant added to U, right?
That's because you only care about the derivative of u for the dynamics. U by itself never contributes to the dynamics. Therefore, you can add a arbitrary constant. Doesn't matter.
No, no, no. But like the points where the this thing occurs, the limit, what do you call this? Limit points that
Yes.
occur equal to ux, right?
Yes.
When you add some arbitrary constant to u,
You add it to both e and u. You get an e prime. Then that's all.
yeah, yeah, because yeah, yeah. Okay, yeah. Mhm. So overall
Hmm.
thing, yeah. Okay. So in the integral, we regard x as a function of u, unlike earlier, where
Hmm.
we regarded u as a function of x. Also, x of u is a two valued as is clear.
From the graph.
Mhm. Then we write x of u equal to x1 of u for x greater than x1 and less than 0, and
Hmm.
x2 of for x less than x2 and greater than 0. Yeah, that's clear. Yeah, and further we replace dx by du into du. So our equation changes as the limits of integration in terms of u initially becomes e to 0 and then 0 to u, e. Okay, so here it's 0 to e and then e to 0. So you get dx2 by du into du by under root e minus u, and here dx by du into du by under root e minus u. Okay, so overall it becomes dx2 minus dx2 by minus dx1 by du into du divided by under root e minus u.
Hmm.
So we have a hat here.
So it's
So
pulled
both
out of
sides
a hat. Sudeshna
okay.
ma'am style.
Okay. So both sides are now divided by under root alpha minus e. Okay. Alpha is a parameter and integrated with respect to e from 0 to alpha. I write it T divided by under root alpha minus E dE equal to under root 2m. Here also write this thing under root alpha minus E dE. Okay. And we're changing the order of integration. So you get under root 2m 0 to alpha dx 2 by du minus dx 1 by du into du, and it's 0 to u to alpha.
Yeah, this I could not understand why it's not till E or whatever.
You take du there and then du by e minus e to e minus u.
0 to E. Ah, okay, no, I mean, in the end, we should have a new company. अच्छा. Okay, it's fine, right? So what you're doing is, in the first case, you are integrating so you're integrating the variable du first.
Mm-hmm.
So when you integrate the variable du, whatever expression you get in the end will be in terms of E, because the limit of integration is E.
Mm-hmm.
And then whatever expression you get, and whatever expression was already there in E, you multiply them and you integrate it with respect to dE. And finally, the expression you get should be in alpha, correct?
Yeah.
Now you've swapped it. Now what you're doing is you're integrating dE first. So when you integrate dE first, your limit of integration should end at U at least.
We integrated till alpha.
So you're integrating it till alpha, so that whatever expression you get, yeah, actually maybe it could have been U also. Okay, I'm not so sure. But at least what I understand now is that why both of them should have alpha and not E.
Yeah, because the final thing has alpha.
Yes, so you could not have had E, because E has to get integrated out, and you're first integrating E, so it has to be till either alpha or U. Now I don't know the logic for the rest of it so clearly. Anyway, so you can take a minute or moment to think about it, otherwise we can move on. I think last time also we had the same problem, but we moved on.
Okay, so thus we get T d divided by under root alpha minus E, okay, this thing, equal to pi into this thing called pi into under root 2m, and there you get x2 alpha minus x1 alpha minus x2 0 minus x1 0. Okay. And we take x2 0 to be 0. Okay, so replacing alpha with u, okay, x1 and x2 are function of u, we get x2 u minus x1 u equal to 1 by pi under root 2m 0 to u t dE by under root u minus e. Okay, simply replace alpha by u. So x2u and x1u are still indeterminate. Thus, there are infinitely many u, which is function of u of x, which satisfy the time period dependence on u. If we assume that the curve u equal to u of x is symmetric about x equal to 0, then x1 of u equal to minus x2 of u, the same as x of u. Then we get x of u equal to 1 by 2 pi under root 2m, 0 to u. Make it symmetric, so x1 of u equal to minus x2 of u.
Twice हो गया.
Yeah. So it's 2 times this thing. Okay. So yeah, fine. So you get t of e dE by under root e minus e. Yeah. That was it. ठीक है, और करना है क्या?
हाँ वो तो रिवीजन किया तूने अभी, वो तो करेगा हुआ था पहले.
Okay. So the next thing is
और फिर भी याद नहीं था मुझे.
okay, the reduced
अरे
mass. Okay.
yes.
So the potential energy of interaction of two particles depends only on the distance between them. So Lagrangian therefore is half m r dot square r1 dot square plus half m to r2 dot square minus u of r1 minus r2 more. We let r equal to r1 minus r2. Let the origin be at the center of mass. Then m1 r1 plus m2 r2 equal to 0. Then use this to we get R1 equal to M2R divided by M1 plus M2 and
Hmm.
R2 equal to M1R divided by M1 plus M2.
Hmm.
Substitute this in the Lagrangian. So you get L equal to half M and
R dot.
R dot minus U of R.
Hmm.
Yeah, so U of R and R dot. R dot will be R1 dot, right? R dot, it should be R dot square or something, right?
Should be R dot square.
Okay.
Yes,
Where
yes.
M equal to M1 M2 divided by M1 plus M2, where it is the reduced mass.
Hmm. Correct.
Okay. So remark, this reduces the two-body problem, Lagrangian to that of a single particle in an external field, symmetric about a fixed origin.
Hmm.
We have another remark. The solution R of T entails solution R1T equal to M2RT by M1 plus M2 and R2 of T. Okay. Solution R1T equal to M2RT by M1 plus M2. This is clear. And R2T. Okay, so what does this mean? Is once you know R of T, then you can find R1 of T and R2 of T, right?
Yes.
Okay. So next thing is the motion in a central field. So
Hmm.
the central field is one in which the potential energy depends only on the distance of r of the particle from some fixed origin. So the free is thus, what is this thing?
Force.
The force is thus F equal to minus del E by del R, which is minus del E by del R into R by R. Okay, this is the
Unit
direct.
vector. Hmm.
Yeah, as we had already seen, angular momentum defined with respect to the
Center of the field.
center of the field will be conserved. The angular momentum of a single particle is m equal to r cross p. Since m is constant, the radius vector is always in a plane perpendicular to m. Okay, that's fine. Thus the motion is always determined, thus the motion is always constrained to a plane.
Hmm.
The radius vector is always in a plane perpendicular to m.
तो एक डिग्री ऑफ फ्रीडम गायब होगी ना आर की.
Ha 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 ha. Fine. So the motion is always constrained to a plane. So using polar coordinates, we can write L equal to half m r dot square plus r dot r square phi dot square minus e of r.
Hmm.
Now, L is independent of phi explicitly. Okay, you take one for coordinate away. So you get d by dt del L by del phi minus equal to del L by del phi dot equal to del L by del phi equal to 0. So from here you will claim that this thing is conserved or something. So earlier, any generalized coordinate that does not appear explicitly in the Lagrangian is called this. The corresponding generalized momentum is an integral of motion. Here, phi equal to m2. What is p phi
mz.
equal to
P phi
mz?
momentum corresponding to phi is the angular momentum along
Yeah,
z.
yeah. So from the law of conservation of momentum, we have m equal to mr phi dot equal to constant. So geometrically, the area of sector bounded by two neighboring radius vector is half r into r d phi equal to dt. So m equal to 2m f dot. Um, half r into r d phi equal to df.
क्या हो गया?
So suddenly we are talking about this radius and area vector. mr phi dot equal to constant.
अरे
M
वो
is
लिखा है
constant.
हाफ बेस इनटू हाइट लिखा है ना ऊपर.
Okay.
तो
Okay. R phi dot is constant. So r into d phi equal to some constant time dt, right?
तो dm by dt is 0.
dm by dt is 0, yeah.
So d by dt of r phi dot should be 0,
Mhm.
and
No, Atul, I think it comes from the fact that R phi dot is constant. So R into d phi by dt equal to constant. So R
Hmm.
into d phi equal to constant times dt. Now that constant time dt and other things we have taken together called df, where d and f dot where that will be two like m capital M by 2m, right?
हमने कुछ पोपट किया अरे यू हाँ ठीक तो यार यू जस्ट डिफाइंड हाफ आर इनटू आर डी फाई टू बी डी एफ ठीक है
Yeah,
if you have this definition and half r is the height r d phi is the base
yeah, exactly.
ठीक है of that triangle and half is so half into all of these gives you the area so that you call df so that is the
Yes,
change
yes.
in the sectorial area now the derivative of this so df by dt is what half r square d phi by dt and this is related to m by this expression so that implies m is equal to 2m f dot correct
Yeah,
so that is all
yeah, yeah. So this constancy of m implies f dot is constant. So this is k
yeah
plus
plus
6.
second
Yeah, that the sectional velocity will be constant.
hmm.
Okay,
Sectorial velocity
okay. So the solution to this central field problem. So we use अबे यार ये छिंके साले से बाहर कुछ इनका चल रहा है. हाँ, okay. The solution to the central field problem. We use the conservation of energy and angular momentum. So E equal to half m r dot square plus r square phi dot square plus u of r.
hmm.
ठीक है?
Hmm.
So this is right as half m r dot square plus half capital M square by small m r square plus u of r. Okay, I can't see this how, where it's coming. M is 2m f dot and f dot is capital M
इसमें
is
डाल
m r phi dot.
अरे m
Yeah,
m
yeah,
r
yeah.
phi dot होता है ना
M
तो
square
वहीं से
r
आ जाएगा बस
square divided by m r square. Okay, fine, fine. Okay,
हाँ
yeah. So that's what is that. Okay, and from there you get r dot equal to dr by dt, and that
हम्म
thing is 2 by a small m e minus e of r minus m square by small m square r square. So from here we get
हम्म
time as a function of r. So also from m equal to mr phi dot d phi equal to m dt by mr square. Okay. So finally you get phi as a function of r. Okay.
हम्म
Fine. E is a
हाँ
function
मस्त
of
है
r. Okay. And m equal to m or phi dot. So here we get t as a function of what r, right?
we get phi
And
as a
r and
function of r
R and phi dot are related. So here you get t as a function of r as a function of t. So using this relation, you can get phi as a function of t. Okay, fine. Okay,
what
now
are you saying Kishore I
so
didn't follow what happened
yeah, yeah. So we have this equation
don't
of
you use your mouse pointer to say what equation you are referring to it's easier
yeah, yeah. So you can see here like we,
I
here we have
don't see a mouse pointer
you can't see my mouse pointer.
no acha okay never mind you say the equation then maybe I'll understand
Okay, so we have this equation t equal to integral of dr by something plus constant. So
yes
from this equation we get t as a function of r
yes
or r as a function of t.
yes
Okay. Now next I have capital M equal to a small m or phi dot. So using this constraint I can get phi as a function of t, which is the next equation, or phi as a function of r.
to be easier than that. So you have dm no you have d phi by dt equal to something. So d phi is equal to m dt by mr square. You replace no. How did you get this final equation? I don't see it very clearly. So if I multiply dr, if I write m by r square over here,
So here we have dr, right?
let me look at my own notes because I can't move when you're looking. So just give me a second. I'm also thinking. You also think, and if you find a clear explanation in which you can explicitly derive it, you
Yeah,
can.
Atul, look here. So we have here
Actually, found it. Sorry,
d5
just a second.
d5 m dt by mr square.
What?
d5 equal to, we have this equation d5 equal to m dt by mr square.
d phi equal to m dt.
Capital M dt by small mr square,
Yes.
right? So,
Yes.
and we have the equation for capital T. Capital T is integral of whole thing. So dt will
Capital
be,
T.
no,
Okay.
sorry, just T. Just T is the integral of whole thing. So
Yes.
dt integral removed, right?
Okay.
Yeah. So you have d phi equal to m integral removed the whole thing divided by a small m r square,
ठीक है, right, obviously. So yeah,
right?
sure.
Now we have phi equal to the integral removed of the whole thing.
Right, right, you're right. ठीक है, sure. Okay, cool. Thanks.
So
That's my
here
mistake.
we have this remark that phi varies monotonically with time, and since phi is a constant, this implies phi dot never changes sign. Mm, Phi
Phi
varies.
varies monotonically with time. So d phi, ठीक है ना, d phi is equal to m dt by mr square. All of these are positive.
Mhm,
So dt is going to, so sign of dt and d phi are linked. So it varies monotonically with time.
mhm.
That is correct. And since phi dot is constant,
So phi
it
never changes.
implies phi never changes time sign.
Phi dot never changes
Okay, so
sign.
it's varying monotonically and phi dot is constant. Okay. But why is phi dot constant?
Uh, because phi dot is capital M by a small m r. No, no. So what? R is a function of time, right? No. But does capital M has
Phi dot.
small r in it?
Capital M is constant, it's conserved. So MR phi dot is, but
M r
R
phi
can
dot.
change, right?
Yeah, but r is changing. So why should phi dot be constant?
Yeah, I also don't know.
I think so. This was like phi double dot or something. Phi dot varies monotonically with time. So phi varies monotonically with time. So d phi by dt will be constant. So d phi by dt will be.
Kishore, I can't hear you anymore.
You can't hear me?
Now it's
Hello.
fine. Tell me.
Yeah. So I think here the phi double dot should be constant or something. Yeah, maybe
Monotonically with time and
monotonically with time. So so that means that it does not like come back or something, right? There is no any
so that
inflection.
is what monotonicity means, no?
Yeah, yeah, yeah.
Time can only change if I starts from a negative value. So
Mhm.
it starts from positive value and it's varying monotonically with time. Phi dot is positive is probably what you need to say.
Mhm.
So then it will never change sign, right?
Mhm. But phi dot equal to constant. And this part is not clear.
This is not clear, you're right. So you should check
Okay.
phi dot constant. Okay, never mind. Okay, we'll see what's wrong with that.
Okay. Further, the radial part
Okay,
of the
then
further the radial part of the motion can be taken as the motion in one dimension. So write u effective as ur plus m square by 2m r square. Okay. So how you get this equation? E effective equal to UR
I also
plus
don't know.
add this extra thing. So m square by 2m r square is called, we call this thing as a centrifugal energy.
So the expression for energy, no, you look at the expression for energy, and that is just the one-dimensional particle plus an effective potential.
Mm-hmm.
You go up and you will see the expression for energy. Go up.
Yeah.
This expression. So you
Mm-hmm.
have E equal to half mr dot square plus half m square by mr square plus ur. So this
Mm-hmm.
entire thing you called an effective potential energy.
Yeah, it's
And
similar to that,
for
that we used to do for like L square by R square terms and taken together as effective potential or something. Like this is
Kishore,
what,
say it again. I could not hear you. The
yeah.
voice is not clear.
Do you remember the hydrogen atom problem and all the central field
Yeah,
problems?
yeah. It's the same thing.
Yeah, yeah. So you call this thing as centrifugal energy, the extra thing.
This comes much before the hydrogen atom problem, by the way, historically anyway.
What?
This comes much before the hydrogen atom,
Yeah,
historically.
yeah, I was just remembering.
Yes, yes. We use a similar thing in quantum also. Yes.
Yeah. So the roots of equal to UR plus m square by 2m r square field, but then field the limits of the radial motion, the distance from the center. Note, this does not imply that the particle is at rest when r dot equal to 0, or since phi dot.
Because phi dot is not zero.
Okay, yeah. Case 1, r has only one bound, so r greater than equal to a minimum thing. The particles comes from and goes to infinity. Okay, so case 2, r is bounded, so r is between r minimum and r maximum. So the path is bounded by corresponding circles. But when del phi equal to 2 pi m by r, from where we get del phi equal to 2 times r minimum to r maximum, and this thing.
But you didn't read it. Does not imply that the path is closed. Bounded by two circles, but it doesn't mean that the path is closed. For
Yeah,
the path to
it's
be
bounded.
closed, you have to have this extra condition that your uh, change in the phase is multiple of 2 pi, where your change in phase is given by this.
Yeah, so this, okay, so basically they're talking about like it will be closed when del phi is rational number times 2 pi.
Yes.
Okay.
I mean, delta phi in one complete going from R max to R min
Mm-hmm.
should be a rational multiple of 2 pi.
2 pi. Okay.
Right? Makes sense also, right?
Yeah, yeah, yeah. Otherwise, like it will never close or something. Yeah.
So the R and the phi will never come back to.
Mm-hmm. Yeah, we encountered similar problem in Jackson also. Remember?
In which question? Actually, we should do the Jackson questions also, at some point.
Yeah, yeah, yeah.
Okay.
Now is the time when we can like try all those things. And, yeah.
Yes, we have to. Okay, go on.
Okay. So delta phi equal to 2 times r minimum to r maximum, capital M dr by r square. Okay, so where,
Yeah, this we already derived, no? We
yeah,
had an equation for d phi in terms of R. That's what we derived.
okay. So we say that after n revolutions, the radial part
Would
would
have
have
completed m revolutions, thus the curve would close.
closed. Okay. Yeah, yeah.
Uh,
Basically, you're talking about this thing that if it's rational, then only the curve will be
uh,
closed. Okay.
mhm.
Yeah. So claim is that there exist only two types of central fields in which all finite motions take place in closed paths. So
Nice.
there is no
Okay.
that central field in which all. Okay, but like how can you see this?
I don't know. It's just a claim. I mean, must be written in the book that this happens, and they probably didn't prove it.
On two types of central case in which all finite motion take place in closed paths. So remark on path construction from repeating segments. Read from the text. Okay. So the remark is when m is not equal to 0, uh, this is rather obvious. So from energy conservation we have half mr dot square equal to E minus E of r minus capital M square by 2mr square, which is greater than 0. Okay,
Yes.
and that implies r square U of r plus m square by 2m, that should be less than er square.
Okay.
Now r can take values leading to 0 if r square U of r, that is less than minus m square by 2m. Where is this e thing going? Okay, r tending to 0, so er square will go to 0. Okay.
Yes. So R can take values tending to 0. Okay.
Hmm. R can take value
Kishore,
leading. Yeah,
are you still
so,
stuck?
yeah. So like R can take values leading to
Arey,
0
in
if,
that inequality, in this inequality, just take the limit R tending to 0.
yeah, yeah, yeah. So er square goes to 0, and so
So
if
ER square will go to 0. Whatever is left is the inequality. So there is nothing
uh,
surprising.
so that is UR must lead to minus infinity either as minus alpha by R square with alpha greater than M square by 2R. Okay, or proportionally to minus 1 by Rn, where n is greater than 2. It's not clear to me now. Okay, 1
So
by R
here,
square. Okay, it's 1 by
so
R
this
square.
entire expression,
Mhm.
huh?
So UR is minus M square by 2M R square. So that's why they have written minus 1 by Rn, where n is greater than 2. Because U of R, why n should be greater than 2?
So because this number has to be smaller, right?
Mm-hmm.
So what does it say? It says that UR must tend to minus infinity either as minus alpha by R square. So if you plug this into the expression for UR, you get minus alpha, right?
Mm-hmm. Yeah.
With alpha greater than m square by 2m, which is this expression. So then the inequality will hold. Basically, you get a bound on alpha if you just substitute this form.
Mm-hmm.
Or you substitute the form minus 1 by Rn. So if you
Mm-hmm.
substitute the form minus 1 by Rn, then your R square gets cancelled. You have in the denominator 1 by, so you get 1 by minus 1 by R n minus 2. So now if
Mm-hmm.
n is greater than 2, that means you will get 1 by R cube or something.
Mm-hmm.
R or R square, R cube, whatever. Now as this number tends to 0, this entire object will tend to minus infinity.
Mm-hmm.
And if this entire object tends to minus infinity, obviously it will be less than minus m square by 2m, which is a finite number.
Mm-hmm.
So that basically tells you that this equation, the condition will hold if you have either this form that you have r square, and if you have r square, your alpha must be greater than m square by 2m, or you have 1 by r cube or 1 by r whatever, and then you don't have any constraints on alpha.
Mm-hmm. Yeah.
Okay.
Okay.
So that
Yeah.
basically is very nice because it gives you exactly what kinds of potentials you are allowed to have, right?
Mm-hmm.
So
Yeah.
that is what he was saying. There are only two kinds which are allowed, either ones with r equal to, n equal to 2 and alpha greater than m square by 2m, or n greater than 2 with minus 1 by r.
Mm-hmm. Yeah. Right.
Yeah, so that actually he just proved that's a very surprising statement, no? The claim above that there are only two kinds of potentials for which.
Mm-hmm.
But that was for closed curves. This is for bounded curves. There is a difference. So anyway, boundedness is a required condition for closeness.
Yeah.
Yeah. Okay.
Mm-hmm.
Okay. I think
So
we can do
next.
Kepler's problem next time. It's okay.
Okay.
Have I even done the Kepler's problem in this? In the
Uh,
notes?
no,
I
I
don't
haven't.
think I have.
So,
Yeah, I haven't done the Kepler's problem. Because this I think I did from Sudeshna ma'am's notes. Okay.
how to
So
start this. Okay. Yeah.
okay, cool. Okay, so thanks, Kishore, for your. Uh, so thanks, Kishore, for your presentation. It was really nice, and
Mhm.
we got to learn things. Obviously, we have to be more prepared every time, but yeah, it's a start. And hopefully next time Diksha will join us. And okay, so do you have anything to add, or we can stop the broadcast?
No, I think we can stop.
All right, thanks, Kishore. See you next time.
Mhm.